Okay, we now talk about the tales of the unexpected topic here. The whole idea here topic is to analyze the effect of fat tail distribution on risk management and loss. The basic premise is that we have been assuming a lot of distribution. Most of the times we assume normal distribution, and the idea to assume normal distribution is that there have been research and they have found that many processes in the world, like height of individuals and many other things, follow normal distribution, and when they see nature following that distribution, they assume that everything would be normal, and this assumption of normality has influenced risk management for centuries. But in these days, it has become quite clear that the distributions are not bell-shaped, that is Gaussian, but instead they have fat tails. Risk management tools such as value at risk are based on assumption of normality, but in a fat-tailed world, war would underprice the catastrophic risk. So we need to understand the history of normality, not just finance and economic, but also for physical and social world, and be able to explain why these distribution are not normal, and explain the implication of these fat tail distribution that we see here. So we'll look at how to understand which distributions to use for asset pricing and risk management. If things are not normal, then what's the way ahead? So economic and financial outcomes are often described by bell-shaped curve, which is also known as normal Gaussian distribution. Outcome in a normal distribution is symmetric around the mean and a probability that steadily decays. The normal distribution is very simple description of world that has shown to describe repeated game of chances, such as tosses of fair coin, bets on lottery, and so on. However, we are fooled by randomness is the question that is posed by Nassim Taleb in his book Fooled by Randomness. The problem is something that seems to be a game of chances. For example, a CEO of a company was selling the firm's collection of art, and he decided to let two houses, and there was an auction. So he understood that it was the game and the right to auction work by a random play. So that was where he assumed that things would behave in a normal way. There is much to it and a lot of stories regarding this. The whole idea about these kind of stories is that we assume things are normal, but the things are skewed. The outcome of game is not normal if we play it repeatedly. There are some irregularities, and the strategic decision making does not follow normal process. So that's the whole idea about different stories and the managemental tales that we have. And interaction creates non-normalness, and it plays in real world like natural world, like earthquake or outrages, financial crisis, depression, and the social and economic system. So non-normality can create havoc if we assume everything to be normal, and that's how things created problem. Let's understand what's the history of normality. So normality in physical sciences, 17th century experiment by Galileo measuring the distance between stars, discovery many of the fundamental properties of normality founded at random errors exhibit distinctive patterns. Small errors are more likely and symmetrical around the true value. In 1713, reversion to the mean was formalized in an experiment by Bernoulli. He drew colored stones from a jar and found that the more he drew, the greater the chances he observed the colors are approximately the true average value of the stones in the jar. The first bell curve was plotted in the second edition of Doctrine of Chances by Abraham de Morvay, published in 1733. The distribution in the de Morvay was a result of fair coin toss. The distribution was so perfect and so beautiful that Morvay gave credit to the Almighty. Then Frederick Gauss and Prairie Simons de Laplace advanced understanding of normal distribution in 1800s. Gauss noticed in a work involving curvature of the earth and accuracy of geographical measurement of Bavarian Hill that the estimate clustered around mean and symmetrical on either side. Gauss also developed the least square statistical method in his attempt to locate the dwarf planet Ceres. He minimized the random error from astrological observation gathered by an Italian monk named Piazzi. Lapla in 1899 developed what is known as central limit theorem. He showed that the large sum of identically distributed mutually exclusive variables is approximately normally distributed. Scientists and mathematicians found that the normal curve highly appealing because it suggested that there are regularities in pattern in real world physical data. The larger the mouth, the more perfect its way. This is how the English statistician French Galion elegantly described the normal curve. And in addition, these identical pattern could be described by two simple metric, mean and variance. So again, one term that what are the two parameters that would be able to describe the Gaussian, the normal distribution? That's just the mean and the variance. And now normality in social system. After discovering physical world, normality was applied to social and biological data. Belgian sociologist Adolf applied normal distribution to human attributes such as height, weight, chest. This is where I came to know the first time about normal distribution. And in the statistical data, like if there is an exam, the average of the class and most of the students would be close to the average. So when there are many examples of such, then it becomes interesting to understand and look at this distribution. That is the normal distribution. So then he continued the normal distribution and used it for different ways for physical and mental attributes. And the name normal distribution did not stick until 19th century. Normality was everywhere and went from being formalized in early 18th century to being socialized in 19th century. It is so named because normal distribution became the new norm. The law of large number was prior truth, and no statistical test of normality has been developed till 19th century. And then we have the normality in financial and economic system. So in the earlier 20th century, quantum physics suggested there are random elements in simplest system. Statistical law replaced classical dynamics. And there is a field called statistical physics. Economic followed this model, replacing classical deterministic model for statistical models. The foundation was laid by Slutsky and Fritsch, and they divided the dynamic of the economy into two elements: an impulse and a propagation. So the impulse and propagation model is central to understanding macroeconomics. To this day, it was the basis of large-scale macroeconomic model developed by Cowles Commission for research in economics and used for policy analysis. So the least square method for estimating economy is propagation matrix and normality of random elements in the economy. Now the errors are normally distributed, which means that this is again an assumption in the regression, and the errors chances of error being away is less, so they'll more or less follow a normal distribution and they'll have particular mean and a standard deviation. So in the years that follow, least square became inseparable from normality, and just with the physical sciences, normality becomes socialized, and it came into the financial world as well. Then Markowitz used the assumption of normally distributed return in the development of modern portfolio theory. He assumed that financial return could be only described by mean and variance, and used to develop the mean variance optimum portfolio. So during 1952, other economists were developing was the basis of asset pricing. Kenneth Arrow and Gregard Debreu developed a general equilibrium economics that allowed for the explicit pricing of risk. And to this date, the assumption of normality in Markowitz and Arrow and Debreu model dominate asset pricing, finance, and economics. The Black-Scholes-Merton model in 1973 is rooted in normality, and Wezek 2002 credit risk model also assume normality. So the people who have used to model many of the phenomena that are assumed to be normal in various models. So that's how it is being used. Now we move to the next part, which is the existence of fat tail and the evidence of fat tails, the implication of fat tail, explanation of fat tail. All are these things that we need to understand. So the question that whether normality truly describes the real world, well, there are evidence against normality, and it's even more in the last 100 years. So in 1870, statistical test of normality in physics world found little evidence to support the theory, and what studies have revealed is the evidence of fat tails. So alternative distribution came into being, like the power law distribution, and the essence of power law distribution integrates the probability of large event away from the mean events in the tail decay polynomially with their size. This is contrast to normal distribution where probability of large event deviate exponential with their size. So polynomially with their size and exponentially with their size, there are two aspects. So that's one part of it. So in other words, fat tail world large event are much more likely to happen. In other words, there are a greater likelihood of a very tall person or a catastrophic hurricane at an extreme high or low return. So this is something you need to understand, that the power law, which uses a polynomial. So let's move to some other theories. So the speed of decay is the tail of power law distribution is governed by alpha is greater than 0. The tail of the distribution fattens as alpha falls. This turns the Gaussian world onto its side. For normally distributed data, mean and variance always capture the data. For power law, the mean and variance may not even exist. This implies that central limit theorem may not apply to power distribution law. So how can be regression to the mean and mean is undefined and the variance is boundless? Mean and variance tell us little in a fat tail world, and the future is subject to large unpredictable event. So it's all about fitting the data into different kinds of distribution, whether it be normal or d power. So evidence of fat tail, let's delve more into this. In the real world, we see evidence of fat tails. The estimated probability densities of California earthquake, several rainfall in UK, solar flares, all indicates that frequency of extreme event was much higher than implied by normal distribution. In statistical term, under normality is a kurtosis of 3. Kurtosis is the measure of peakness of a distribution. Also, people argue that it really measures heaviness of the tail. Higher kurtosis means more variance and fewer extreme deviation, rather than more frequent modest deviation. Higher measure of kurtosis means fatter tail. For the natural system, kurtosis was higher, sometimes much higher than 3. In fact, kurtosis was 3,000 times greater than normal for earthquake. This means that forecasting model was severely underestimating the risk of catastrophic event if normality was assumed. So the evidence holds that one considers the social system and he has to look at frequency and cite those frequency, and there has been Mob Dick who has written the frequency of citation of scientific research and population of people in US cities. The data exhibit fat tail. So the distribution of city grows by Zipf's law and exhibits a sliding pattern. The largest city is twice the size of second 3 times, and so on. So there were some evidences, and when we analyze financial and economics data, again non-normality prevails. Real GDP growth from 1880 to 2008, that's a long time. So Bangkok rice export for the last 1000 years, bank loan for the last 200 years or so, and monthly return from again last 200-300 years, all exhibit fat tails. And they've given us some of the kurtoses of various physical phenomena, and for solar flare it's 585, earthquake it's 8,325, rainfall it's 3.3, and population of US cities is 6,000. So these all implications talk about the fat tails, and we have tried to fit normal distribution with the fat tail, and the normality assumption here is assumed, and we then calculate the fat tails. So what are the implications of these fat tails? Why are they important? So consider insurance. If premiums are based on assumption of normality, catastrophic events are rare and premiums are low. Assume a contract play. If even a 4 standard deviation from mean in 1 year, the premium would be enormously higher if calculated based on fat tail distribution, and the likelihood of being 4 standard deviation is much higher. In fact, the ratio of 4 sigma events versus the implied normal distribution more than 100 times. So this implies that the actuarially determined price of insurance contracts protects against 4 sigma events would be 100 times higher. So what are the explanation of fat tails? And it seems that interaction are at least partially to blame for fat tails. The central limit theorem assumes events are independent, but they are not. Remember, like the girls playing in rock paper scissors, they don't randomly choose scissor, but they choose scissor based on the expectation of their opponent. And the assumption of independence almost certainly violated natural social and economic system. The non-linear dynamics, weather provisions, an interesting example for physical world regarding progression assumption of normal and awareness. In 1904, Bingham examined 7 equations with 7 unknown that provided the foundation of meteorology. The system was complex. Non-linearity arose from interaction between atmosphere and convection. In 1963, American meteorologist Edward Lorenz discovered that a dynamic of non-linear system like weather are highly sensitive to initial condition. Therefore, small changes to weather system can link to dramatically different outcomes. Then, the whole idea is non-linear dynamics, self-organized criticality, preferential attachment, high optimized tolerance, and these are the reasons on why actually interactions are taking place, and that would explain the fat tails that exist. So in that regard, if you look at self-organized criticality, physical laws governing weather system or other self-organized to fragile status, consider a sand pile for example. What does not organize the sand pile grain by grain? It self-organizes into critical state, but system does not conform to central limit theorem. Many avalanche become as additional grains are added, offsetting the effect of extra grains. So one thing can throw the whole system into catastrophe. There are some evidence that equity prices have considered with this phenomena. So if it falls, then it keeps on falling. So the events are not like just normal, but when something happens, other become also related. And then there is something called preferential attachment, which says that social network increases interaction beyond those found in non-linear. So one feature of social system is there are generally large number of poorly connected regions, small number of highly connected. Preferential attachment 1% implies that popularity P gets popularity, increase richer get richer phenomena. And popularity can be a sign of quality or simple succession if a network of characteristics. The preferential attachment explain economic citation, situation law. It also explains the outgrowth of strategy in forms of rocks. So whole idea here is that what's going on in the mob is going to be continued. So things would be working in the same direction as they are, and this is the whole idea about preferential attachment. Then we have highly optimized tolerance. The man nudges a system towards critical state. The system are often referred to as a system of highly optimized tolerance. Fire break is an example. To manage potential forest fire, forest assets where lightning strikes most thin trees are there. In the area where lightning strikes are rare, the forest allows. So the financial crisis offers a second example of highly optimized tolerance. And before the financial crisis, regulators had capital ratio based on their incorrect assessment of risk. Bank Inter overweighted their allocation, and this is the way in which things went bad. So this resulted in a fat tail kind of an event. So those are all reasons on how things are related. Now when we look at the system based interaction, we have to understand that there are some examples of system based interaction which can lead to fat tails. A perfect example of interdependence in the financial system was the financial crisis. Everything to be tied up. Poor credit quality at one bank translated into frozen credit market for other, perhaps healthy banks. Leverage contributed to chaos. Leverage contributed to tail risk as it generated non-linear system-wide responses. Prior to the meltdown, financial firms were consistently increasing risk to reach higher targeted return. The system self-organized on higher risk. Using the sand pile analogy, a single grain of subprime sand was enough to cause the entire sand pile to collapse. It's clear that the financial market likely exhibit all of the above described characteristics: non-linearity, criticality, contagion, and these factors are more prevalent during a crisis. Financial market continue to become more integrated. We can likely expect more non-linearity, more chaos, and fatter tails. Other examples of system-based interaction that can lead to fat tails are sand piles, forest fires, unregulated traffic, eurozone debt crisis, failure of demand, and bank runs. So non-normality and regard to asset pricing and risk management now needs to be explored, and that's the second part here. And it appears that economics and finance theory may have been fooled by randomness. There is a distinct disconnect between theory and reality. The theory is the assumption of normality and the reality is Fat-tail distribution. One thing that it is important to understand is that asset pricing is the distinction between risky and uncertainty. Risk rises when the distribution of future data is unknown. For example, standard deviation is a measure of risk attributing to distribution of return is known. Uncertainty rises when the distribution is unknown or incalculable. However, such financial research in the past 50 years has ignored uncertainty and solely focused on risk. Under uncertainty, there is no single asset price, but a range of asset prices. Under asset price systematic differs from other. In general, the core feature of existing financial model may now need to re-examine and perhaps abandon. Interaction non-linearity replace a single stationary equilibrium kind of a phenomena. In the last 5 years, there have been a way of interest in modeling financial and economic system as complex adaptive network, something like a feedback control. Now, in this regard, we have to now look at our last topic here, which is the non-normality and risk management. Common methods of risk measurement and management such as value at risk rely on assumption of normality and are essentially silent about risk in the tail behavior. A bank could establish 99% vol limit for a trading limit and construct a portfolio with 1% chance. If the regulatory required is based on VOR, then the requirement will be dangerously underestimated. This problem exists even if returns are normally distribution. The bigger problem with VOR is that the fatter tails, the more misleading VOR measures will be high. For example, invest in a portfolio of world liquidity for 300 days or so, then the 99% VOR given a normal distribution is 6 trillion in a day dollar. The estimate increased to 7.8 trillion using actual data in 18.4 if you consider VOR on being 1% of the tail distribution. Thus, VOR used by banks and other underestimated the total risk by a factor of 1.2 to 3. Now, risk manager continued to serve because of its simplicity. However, it continues to surprise firm by not capturing tail risk. For example, JP Morgan developed VOR, announced a loss of 2 billion in May 2012, updated to 4.4 on a credit exposure. I think they are talking about the blue whale here, but they have not described it. The VOR on this portfolio for the first quarter was a mere 67 million. Now, the Black-Scholes Merton pricing model used to for value financial like payoff also assumes returns are normally distributed. If indeed returns are powered or distributed, Black-Scholes model would also be mispriced. For example, volatility smile percent indicators state that employment greater extremities. If underlying distribution of return has fat tail, it provides one explanation for the smile. It would also increase the value of deep out of the call money option relative to Black-Scholes formula and raise Black-Scholes implied volatility. The VESAC credit risk model also assumed normal and mispriced catastrophic risk. The model used to determine bank capital requirement under internal rate Basel II framework using GDP growth rate assumed to be normally distributed, a factor indicating the bank would approximately 3% of capital buffer to cover loss. However, based on actual failed fat tail distribution of GDP over the last 300 years, the capital buffer should actually be around 12%. One study of mispricing in the VESAC model indicates that capital requirement would be 20 to 85% higher, assuming fat tails. As for the normality assumption in the Black-Scholes model result in significantly mispricing of catastrophic risk. Both the VESAC credit risk model and Coppola approach to modeling credit risk misprices catastrophic risk. In general, financial firms need to totally rethink risk management model to estimate potential losses required, and they should not rely on normality. Clearly, if distribution are fat tail, economic and financial model are understating tail risk. So that was the whole idea, understanding that it's about fat tails, understanding the limitations of normal distribution and the road ahead for us. I hope this added some value to your knowledge base. Thank you for listening.